All right, so we're going to talk about properties of the normal distribution in statistics. So pulse rates of randomly selected adult males have a distribution with a mean of 70 beats per minute, or BPM. We use the little U looking shape there, it's called the Greek letter mu, to denote a mean. The standard deviation of the distribution, which we denote as sigma, which looks like an O with a little tail at the top, is about 11 beats per minute. Making the reasonable assumption that the distribution of pulse rates is approximately normal, we can picture it as it is shown in the figure. Because all normal distributions have the same bell shape, knowing the mean and standard deviation of a distribution allows us to know much about where the data values lie. So you can see down here on the graph, we've got our mu and we've got our sigmas. So for example, if we measure area under the curve in the figure, we find that about 2/3 of the area lies within one standard deviation of the mean, which in this case is between 70 minus 11 equals 59 beats per minute and 70 plus 11 equals 81 beats per minute. So here's our mean, and our standard deviation was 11 points. So that means it's one standard deviation on either side. Therefore, about 2/3 of adult males have pulse rates between 59 beats per minute and 81 beats per minute. Similarly, about 95% of the area lies within two standard deviations of the mean, which in this case is between 70 minus 22, two standard deviations would be 2 times 11 equals 48 beats per minute, and 70 plus 22 would equal 92. So we can see here between 48 and 92, that would be 2 standard deviations, because here's 1, and then there's 2 standard deviations. And then from here it'd be 1 and 2 standard deviations. We conclude that about 95% of adult males have pulse rates between 48 beats per minute and 92 beats per minute. A rule called 68, 95, 99.7 gives guidelines for the percentages of data values that lie within 1, 2, and 3 standard deviations of the mean for any normal distribution. The following states the rules in words, and the figure shows it visually. About 68%, more precisely 68.3%, or just over 2/3 of the data values fall within one standard deviation of the mean. About 95% of the data values fall within two standard deviations of the mean, and about 99.7% of the data values fall within 3 standard deviations of the mean. And here you can see our 1, 2, and 3 standard deviations, and 1, 2, and 3 standard deviations on either side of the mean. So example 1, the tests that make up the individual parts of the SAT and the GRE, the LSAT, and GMAT are designed so that their scores are normally distributed with a mean of mu equals 500 and a standard deviation of sigma equals 100, and a range from 2 to 800, or 200 to 800. So let's interpret this statement. So from the rule of 68, 95, 99.7, about 68% of the students have scores within one standard deviation, which was 100 points, of the mean of 500 points. That is about 68% of the students score between 400 and 600. Because if we take our 500 points and we subtract out the 100, we get 400, and 500 plus 100 will get us 600. About 95% of students score within 2 standard deviations. So 2 times 100 would get us 200 points of the mean, or we can take our 500 and we can subtract 200 to get 300, and add 200 to 500 and get 700. So That means about 95% of the scores will be between 300 and 700. And about 99.7% of students score within 3 standard deviations, or 300 points, because 3 times 100 would get us 300 of the mean. Or we're taking 500 minus 300 gets us 200, 500 plus 300 will get us 800. The figure shows this interpretation graphically. So we can look here. Here is our mu, 1 standard deviation, 2 standard deviations, 3 standard deviations. And it goes the same on the other side. And you can see in the first one, it's 68% of the scores are here. And then 95% of the scores are between 3 and 7, and 99.7 go from 2 to 800. Note that the horizontal axis shows both actual scores and the distance from the mean in the standard deviations. So you can see the actual scores here, and you can also see how many standard deviations it is. Example 2, detecting counterfeits. Vending machines can be adjusted to reject coins above and below certain weights. The weights of legal U.S. quarters have a normal distribution with a mean of 5.67 grams and a standard deviation of 0.07 gram. If a vending machine is adjusted to reject quarters that weigh more than 5.81 grams and less than 5.53 grams, what percentage of legal quarters will be rejected by the machine? So a weight of 5.81 grams is 0.14 grams, or 2 standard deviations above the mean. So how do we find that? We take 5.81 and subtract our mean of 5.67, and we get the 0.14. And 0.14 divided by 0.07 gets us 2. The weight of 5.53 grams is 0.14 grams, or 2 standard deviations below the mean. So again, if we take 5.67, subtract out 5.53, we end up with 0.14. Divided by 0.07, we get 2. Therefore, by accepting only quarters within the weight range, the machine accepts quarters that are within 2 standard deviations of the mean and rejects those that are more than 2 standard deviations from the mean. By the rule, about 95% of legal quarters will be accepted and about 5% of legal quarters will be rejected. So I've actually taken coins to a bank to put it in the machine where it will count the money. And it has actually rejected some of the legal quarters I have because they had like nicks on them, which I think those nicks took out some of the weight of the quarter because we're not talking very much here. And it took out enough that it rejects it out of the actual legal weight. So applying the rule, we can apply the rule again to find approximate answers to many questions about the frequencies of data values in a normal distribution. Consider an exam taken by 1,000 students for which the scores are normally distributed with a mean of mu equals 75 and a standard deviation of sigma equals 7. How many students scored above 82? A score of 82 is 7 points, or 1 standard deviation above the mean of 75. So when we're looking at that score of 82, subtract 75, and we get 7 points. 7 points is our standard deviation. So according to the rule, that tells us that 68% of the scores are within 1 standard deviation of the mean. Therefore, remember, we're looking at how many students scored above 82. About 100 minus the 68%, because that's a score of 82, will get you 32% of the scores are more than 1 standard deviation from the mean. Now, half of that goes on one side of the mean, and half of it goes on the other. So half of 32, or 16%, of the scores are more than one standard deviation below the mean, and the other half are one standard deviation above the mean. So we conclude that 16% of 1,000 students, or 160 students, because we multiply 16% times 1,000, scored above 82 on the exam. Similarly, suppose we want to know how many students scored below 61. A score of 61 is 14 points, or 2 standard deviations below the mean of 75. So again, 75 minus 61 will get us 14. Our standard deviation was 7. 14 divided by 7 is 2. So we have 2 standard deviations below that mean of 75 with a score of 61. Well, the rule tells us that 95% of the scores are within 2 standard deviations of the mean. So there's about 5% of the scores are more than 2 standard deviations from the mean. Now remember, you have 2 sides of your graph. So if you take half of that 5%, that means 2.5% of the scores are more than 2 standard deviations below the mean. So we conclude that about 2.5% of 1,000 students, or multiply those together with the decimal 0.25, we get 25 students scored below 61. Because 95% of the scores fall between 61 and 89, we can say that the scores outside this range are unusual because they are relatively rare. So here you can see your 2 graphs where we're looking at the standard deviations. We're looking at 1 standard deviation, 2 standard deviations, and there's your third one. And so it's showing you the scores that were in between the 2 standard deviations and then those that are on the outside. So we're looking at in this side here, the 68% and then the 95%. In statistics, we often need to distinguish values that are typical or unusual or usual from values that are unusual. By applying the rule, we find that about 95% of all values from a normal distribution lie within 2 standard deviations of the mean. This implies that among all values, 5% lie more than 2 standard deviations away from the mean. We can use this property to identify values that are relatively unusual. Unusual values are values that are more than 2 standard deviations away from the mean. So example 3, consider again the question of whether you should advise a pregnant friend to schedule an important business meeting 2 weeks before her due date. Actual data suggests that the number of days between the birth date and the due date is normally distributed with a mean of mu equals 0 days and a standard deviation of sigma equals 15 days. How would you help your friend make the decision? Would a birth 2 weeks before the due date be considered unusual? Well, your friend is assuming that she will not have given birth 14 days or roughly 1 standard deviation before her due date. But because this outcome is well within 2 standard deviations of the mean, it is not unusual. By the rule, the day of birth for about 68% of pregnancies is within 1 standard deviation of the mean, or between minus 15 days and 15 days from the due date. This means that about 100 minus 68% equals 32% of births occur either more than 15 days early or more than 15 days late. Therefore, about half of this 32%, or 16% of all births, are more than 15 days early. You should tell your friend that about 16% of all births occur more than 15 days before the due date. If your friend likes to think in terms of probability, you could say that there is a 0.16 or about 1 in 6 chance that she will give birth on or before her meeting date. And we can see here in the graph what we're talking about. So in this percentage parts here, this is where most of the births are going to happen, and then it's 16% on either side because that's 32% total. All right, so example 4 are pulse rates of adult females. So pulse rates of adult females are normally distributed with a mean of 74.0 beats, or 74.0 beats per minute, and a standard deviation of 12.5 beats per minute. What is percentage of adult females with pulse rates below 49.0 beats per minute? So a pulse rate of 49.0 beats per minute is below the mean of 74.0 beats per minute by 25. And we know that because we take 74 and we subtract out 49 and we get 25 beats per minute, which is 2 standard deviations below the mean because 25 divided by 12.5, which is our standard deviation, equals 2. According to the rule, about 95% of the data values are within 2 standard deviations of the mean. Therefore, about 2.5% of the data values are more than 2 standard deviations below the mean, and about 2.5% of the data values are more than 2 standard deviations above the mean. Because if we're looking at 95%, that means there's 5% left, and you have to split that in half to go on either side of the graph. Therefore, about 2.5% of pulse rates of adult females are below 49.0 beats per minute. So, the standard scores, we're using the rule, and it applies only to data values that are exactly 1, 2, or 3 standard deviations from the mean. For other cases, we can generalize this rule if we know precisely how many standard deviations from the mean a particular data value lies. The number of standard deviations a data value lies above or below the mean is called its standard score, or z-score. It's often represented with the letter z. For example, the standard score of the mean is z equals 0 because it's 0 standard deviations from the mean. The standard score of a data value 1.5 standard deviations above the mean is z equals 1.5. The standard score of a data value 2.4 standard deviations below the mean is z equals negative 2.4. So when it's above the mean, it's going to be positive. When it's below it, it's going to be negative. So to compute a z-score, or they're calling it standard scores or z-score, either one works. So to compute one, the number of standard deviations a data value lies above or below the mean is called its standard score or z-score. I will probably refer to it more as the z-score. And it's defined by z is equal to standard score equal to the data value minus the mean divided by the standard deviation. So the standard score is positive for data values above the mean and negative for data values below the mean. We commonly round the standard score to 1 or 2 decimal places, depending on the precision of the data. Example 5. The standard Binet IQ test is scaled so that its scores have a mean of 100 and a standard deviation of 15. Find the standard scores for IQ scores of 85, 100, and 125. So we calculate the standard scores for these IQ scores by using the standard score formula with a mean of 100 and a standard deviation of 15. So remember our formula. The standard score is going to be z equals, it is our score of 85 minus our mean divided by the standard deviation. So at the top, 85 minus 100 is negative 15, and make sure you put them in the right order. Divided by 15, well, that equals negative 1. The standard score for 100 is 100 minus 100 over 15 equals 0 divided by 15, which equals 0. And the standard score for 125 is 125 minus 100 over 15, which equals 25 over 15, which will get us about 1.67. So notice that the 100 and the 15 over here don't change. The only thing that's changing on this problem is the number you're looking for the score on. We can interpret these standard scores as follows. 85 is one standard deviation below the mean because it was negative. 100 is equal to the mean because it had the deviation of, let's go back, it had a deviation, or a standard score of 0, sorry, not deviation, but z-score of 0, so it means it's equal to the mean. And 125 is 1.6 standard deviations above the mean. The figure shows these values on the distribution of IQ scores. So we can see where all of the scores lie. Here's the 100, here's the 125, and here is the score of 85. Standard scores and percentiles. So the nth percentile of a data set is the smallest value in the set with the property that n% of the data values are less than or equal to it. A data value that lies between two percentiles is said to lie in the lower percentile. We can convert standard scores to percentiles with computer software or a standard score table, such as the table A1. Now I'm going to give you the table in any way that you need it as far as the exam goes, and you have it on your handout for doing your homework, plus it's in the video, so you can use it there. To use the table, notice that for each standard score between -3.5 and 3.5, the table gives the proportion of values in a normal distribution less than or equal to that value. So you can then convert the proportion to a percentile. So here are the scores. So we've got negative scores that are here and the positive scores that are here. So we are looking at, this is the negatives and this is the positives. So this is what the tables look like. So you can use these to find them. And when you're looking up a number, you're going to use this column first and then use this one. And then you'll use if you have a negative number, you use this column and then you'll use this one up here. So, and I'll explain that as we go. So using the table, for example 6, we're going to find and interpret the percentiles that correspond to the standard score of -1.7 and 0.15. So for -1.7, we are going down this way, we look for -1.7, and because it has a 0 for the second decimal value, we go to the 0 here, so 0.00, and this is our value right here. So a standard score of z equals -1.7 appears in the left column on the left page of the table. The next column shows that for this exact standard score, the proportion of values to its left is the 0.446, or changing it to a percentage, we move our decimal place over 2 places and we get 4.46%. Therefore, a data value with a standard score of z equals -1.70% represents the 4.46th percentile, meaning that 4.46% of all data values in a normal distribution have a standard score less than or equal to that. So that means that any values below it are less than or they're in that 4.46% of all the data values. All right, let's look at B. So here again we have the table. Now it's positive, so we're using the right page of the table. The first 2 digits of the standard score are 0.1. So we look for the row with 0.1, and then we go over to find the 0.05. And where those line up and intersect, that's our score right there. So the first 2 digits are the 0.1. We look in that row, and then notice that this is the second row. And then the third digit, z, is equal to 0.15. It's a 5, but because it comes in the hundredths column, it represents the value of 0.05. Therefore, you look across the table to the column, which shows that proportion of the values to the left. Now remember, this is a decimal. We can change that to 55.96. Therefore, a data value with a standard score of z equals 0.15 represents the 55.96 percentile, meaning that 55.96% of all data values in the normal distribution have a standard score less than or equal to 0.15. Cholesterol levels. So cholesterol levels in men 18 to 24 years of age are normally distributed with a mean of 178 and a standard deviation of 41. So what is the percentile for a 20-year-old man with a cholesterol level of 190? Well, if we go look at our standard score for a cholesterol level of 190, the z-score, which is our standard score, is the data value minus the mean over standard deviation, because 190 is not going to land into our table. So we have to take our data value, which is 190, minus the mean. The mean was given to us at 178, and then take that and divide it by 41, which is approximately 0.29. Well, that falls into our table. So we can go to 0.2 and then over to the 9 for our third digit, and we get 0.6141, which changed to a percentage will be 61.41 percentile. Part B asks what cholesterol level corresponds to the 90th percentile, the level at which the treatment may be necessary. So the 90th percentile corresponds to a proportion of 0.900. The closest number to this in our table is 0.8997, which is found in the row corresponding to z equals 1.2 and 8. So here we're looking at finding the percentage. And when you're looking for that, you've got to find the one that's closest to it. This one says 90.15, so that's 15 above 90. And this one is 0.8997. So when you're looking at this, you're only missing this 0.003, and this is 0.0015. So this one is closer to 90 than this one. So you have to just really look at the data values to see how close they are to the 90. So because of this, I can look at the score, and this goes over to 1.2, and it goes up to 0.08. So that's where I get the 1.28 z-score. That is the 90th percentile is about 1.28 standard deviations above the mean. Given the mean cholesterol level of 178 and the standard deviation of 41, a cholesterol level 1.28 standard deviations above the mean is the mean plus 1.28 standard deviations times our 41, that's our standard deviation there, will get us 230.5. So you're taking your mean cholesterol and multiplying by the standard deviation that it is, 1.28. Our standard deviation is 41, so multiply those together to get your total score there. So the 90th percentile begins at a cholesterol level of about 230.5. So anyone with this level or higher might need treatment. IQ scores, example 8. So IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. What are the IQ scores for people in the 75th and 40th percentiles on IQ tests? So using our table again, we can see that the 75th percentile falls closest to a standard score of, here is our 75th. Again, we're looking at, this is 0.0014 away from 75, and this is 0.0017. So this one is closer to 75. So that tells us it's at 0.6 and 7. So it's 0.67 for our z-score. That corresponds to an IQ that is 0.67 standard deviations, or about 0.67 times 15, because our standard deviation was 15, so we multiply those together to get the number equal to 10 points above the mean. So we can say that the 75th percentile has an IQ of 100 plus those 10 points, because our 100 is our mean, plus the extra 10 equals 110. Now, the 40th percentile is going to work similar to the 70th. So we're looking at approximately negative 0.25. So we have to go looking for 40%. So here we see some 40s, but we've got to get the one closest to 40. So 0.4013 is closer to 40 than 0.3974 or 0.4052. So that tells us we're going to end up with negative 2, and up we go to 0.05. So negative 0.25, or a score that is 0.25 times 15 equals 3.75. So about 4 points below the mean of 100. So a person in the 40th percentile has an IQ of 100 minus 4, which equals 96. So women in the U.S. Army. The heights of American women ages 18 to 24 are normally distributed with a mean of 65 inches and a standard deviation of 2.5 inches. In order to serve in the U.S. Army, women must be between 58 inches and 80 inches tall. What percentage of women are ineligible? So make sure you read that correctly. Is it ineligible or eligible to serve based on their height? This means that they cannot be eligible if they're ineligible based on their height. So the standard scores for the Army's minimum and maximum heights of 58 inches and 80 inches are, for 58 inches, we have to take our 58 minus our mean of 65 divided by our standard deviation of 2.5. Well, 58 minus 65, oh, that should have a negative sign right here, minus 7 over 2.5 equals negative 2.8. For 80 inches, it's 80 minus 65 over 2.5 equals 15 over 2.5, which equals 6. So the table shows the standard score of negative 2.8, and then corresponding with 0 gets us to the 26th percentile. A standard score of 6 does not appear in our table. So remember, it only goes to like negative 3.5 to 3.5. This means it's above the 99.99th percentile, which is the highest percentile shown in the table. So we conclude that 26% of all women are too short to serve in the Army, and fewer than 0.01% of all women are too tall to serve in the Army. So there's not very many who are too tall to serve. Altogether, fewer than about 0.27% of all women, or about 1 out of every 400 women, are ineligible to serve in the Army based just on their height. Now, as we move forward, we're going to go towards probability. Suppose you pick a baby at random and ask whether the baby was born more than 15 days prior to his or her due date. Because births are normally distributed around the due date with a standard deviation of 15 days, we know that about 6% of all births occur more than 15 days prior to the due date. For an individual baby chosen at random, we can therefore say that there's about a 0.16 chance, or about 1 in 6, that the baby was born more than 15 days early. In other words, the properties of the normal distribution allows us to make a probability statement about an individual. In this case, our statement is that the probability of a birth occurring more than 15 days early is about 0.16. This example shows that the properties of the normal distribution can be restated in terms of ideas of probability. In fact, much of the work we will do throughout the rest of the text is closely tied to ideas of probability, which is what we will get into next.